Hello, everyone. I would like to thank the TQC committee for allowing me to speak at the conference. My name is Pablo. I'm from the Sydney group, and today I'll be talking about the XZZX surface code. I want to give a huge thank you to all my supervisors, David Tuckett, Ben Brown, Steve Bartlett, and Steve Flammia, who allowed me to be part of this awesome project. The essence of the work that we did is to slightly tweak a standard quantum error correction code in order to take advantage of the structure of the noise, which is actually occurring in the qubits being used to build a quantum computer. We actually found very high thresholds for all single qubit Pauli channels. These thresholds seem to match and even exceed the hashing bound of a noisy channel. We also demonstrated improved sub-threshold scaling of the logical failure rate, and finally briefly discussed how to maintain these advantages when performing fault-tolerant quantum computation. I'll be expanding on this concept as I go along the talk, but first I want to quickly review some concepts of quantum error correction. The grand aim is to be able to build a functioning quantum computer, but the problem is that qubits are very noisy and decohere quickly. It turns out that we can actually tolerate noise on individual qubits, which we call the physical qubits, by using quantum error correcting codes, which store the logical information in a larger structure of the code. In the case of the surface code, the logical qubits are composed of these strings of physical qubits which wrap around the surface of the code. So that roughly, we need a line of errors to damage our stored logical information as opposed to a single error on a physical qubit. In practice, the procedure of error correction with stabilizer codes, such as the surface code, is as follows. We encode some logical information in a system of physical qubits. Then some error process occurs, and we gain information about the error process by using stabilizer measurements. These give a -1 measurement outcome whenever there is an odd parity of errors nearby. These stabilizer measurements form what we call the syndrome of the code. We then apply a decoding procedure to the syndrome and obtain a recovery operator, which we apply to the error state of the code to get a new state, which is now back into the +1 eigenspace of the stabilizer group. We then compare this new state to the original state in terms of logical space, and if we're not in the same logical state as the original state, then a logical error has occurred. Now, in the standard surface code, we put the qubits, the physical qubits, on the vertices, and the stabilizers are as follows. So we have X-type stabilizers on the dark faces, and these measure the parity of nearby Z errors, while we have Z-type stabilizers on light faces, and these measure the parity of nearby X errors. The logical operators are simply a horizontal of X operators and a vertical of Z operators. We put these boundary terms faces here on the edges to make the code planar so that we can actually implement it in a chip. Now, you can imagine some errors occurring on the qubits, and we go in and measure the stabilizers on every face to get the syndrome of the code. You can see that these are these -1 measurement outcomes, or as we like to call them, defects. They always live at the endpoints of a string of errors. The job of a decoder is to grab these -1 measurement outcomes and return a suitable correction operator or recovery operator. An efficient way that we can do this in the surface code is to match nearby defects so as to minimize the total distance between pairs of matched defects in the grid. This approximates in an efficient way the most likely error strings which could have led to the observed syndrome. This decoding algorithm is known as minimum weight perfect matching and is considered as a decoder which could be used in practice in a quantum computer. Another decoding algorithm which we used in our results, is known as a maximum likelihood decoder, which literally calculates the most probable logical coset of equivalent errors. Of course, in practice, this would be too slow, but an approximation is due to Bravi, Zucara, and Vargo, and it's based on contractions of tensor networks, and they approximate this optimal decoding algorithm. This approximates optimal decoding really well, but it still doesn't really scale efficiently to fault-tolerant decoding where measurement errors become relevant. However, it is still a good decoder to gauge the best performance of a code. Speaking of gauging the performance of a code, a standard figure of merit is known as a threshold. The threshold is simply that point in the physical error rate scale below which we can decrease the logical failure rate to as small a value as we like. The price to pay there is that we increase the size of the code if necessary. To implement any of the exciting algorithms with a quantum computer, we really want to be below threshold. So we're able to take advantage of this reduction in logical error rate and keep the quantum state alive for long enough so that the computation may succeed. I now want to talk about the motivation for our work. So we want to tailor quantum error correcting codes to take advantage of the structure of the noise on particular types of qubits. And this is actually something that David Tuckett worked on during his PhD thesis. The way that we will take advantage of the structure of errors is by looking at symmetries in the code. And it's actually something that Ben Brown and Dominic Williamson have been thinking of for a while now. We'll come back to the symmetry part in a moment, but I want to elaborate what I mean when I say the structure in the noise. It turns out that dephasing errors, also known as phase flips or Z errors, are the most common type of errors in many of the qubits that people are trying to use to build a quantum computer. For example, these are electron spins in silicon quantum dots, and the people that are trying really hard to harness the power of these are scientists at the University of New South Wales, for example. In these qubits, Z errors can occur at a rate that is up to 2,000 times more frequent than bit flips or X errors. Now, a particularly exciting example of biased qubits towards Z errors is these haircut qubits. These are based on superposition of coherent states in a superconducting resonator. Not only are these high quality qubits, but there has been work done in applying gates to them, which preserve the bias of the noise in the qubit. This is very important because if we're trying to take advantage of the bias in the noise, then we don't want it to disappear when we apply gates on the qubits. Now, here's a way that we quantify the bias in our simulations. First, we have here the depolarizing channel where X, Y, and Z errors all occur with a probability, with an equal probability of P on 3, where P, little p here, is a physical error rate. That is the probability of an error on any one qubit. And with probability 1 minus P, we apply no error. Now, the bias noise model looks like this. We now label the probability of an X, Y, and Z error by Px, Py, and Pz. And we quantify the bias in the noise through this bias coefficient here, which is given by the probability of the high rate Z errors over the sum of the probabilities of the lower rate X and Y errors. Two notable limits of this noise channel is when the bias goes to infinity. So this is the case of a purely dephasing noise channel, or the channel where only Z errors are occurring. At the other extreme, we have a bias of 1/2, the depolarizing channel. So we recover back this channel where X, Y, and Z errors are occurring at the same rate, and there is no bias in the noise. Now, associated with the noise channel, we have the concept of the hashing bound. So let's write up our noise channel like this again. And let's call the vector of error probabilities P here, given by that. And let's call the H of P the entropy of that distribution. Then for classical codes, the hashing limit states that the rate at which information is transferred in the channel, capital R, is given as 1 minus the entropy of the distribution. For quantum channels, this is only a lower bound for the rate. Indeed, there's a theorem which states that the hashing bound is achieved with at least one quantum error correcting code. Exceeding the hashing bound has interesting theoretical consequences, such as the superadditivity of coherent information. And there has been work done on trying to develop quantum codes to exceed this bound, but never with a practical implementable code. Now, I should say that for the surface codes which we study, the rate is vanishing. And to calculate the threshold error rate of the hashing bound, we set R to be 0. And so for P, which equals to PHB or P hashing bound, so this PHB is the P value that we compare our thresholds to when we say that we're comparing against the hashing bound. Now, finally, here's the XZZX surface code. So all we do is we take the standard CSS surface code and apply a Hadamard to every other qubit. So you can see that an X stabilizer would go from XXXX to XZZX, and every single light phase Z stabilizer would go from a ZZZZ to an XZZX. And therefore, every single stabilizer in the new code is an XZZX. The reason why we expect it to perform well against biased Z errors is because now every single stabilizer in the new code can detect these odd parity of Z errors nearby, whereas in the original one, only half the X stabilizers could detect the Z errors, which are the most frequently occurring errors. Now, here are the thresholds of the XZZX surface code using a maximum likelihood decoder. What you see on the bottom here is a type of errors. So this here will be purely X errors, and this here will be purely Z errors. While here in the middle, we have the depolarizing channel. On the Y-axis, we're plotting the maximum likelihood thresholds. And in fact, to construct this surface, David had to collect over 100 threshold values, which equals to a lot of compute time. Amazingly, the XZZX surface code matches the hashing bound everywhere on this surface, and even appears to exceed it at the very high bias values in any direction. The best version of the CSS surface code tailored toward bias noise, which is also work from the people here in Sydney, also matches the hashing bound in the direction of the noise it is tailored toward, but falls off significantly in the other directions. Okay, so this is great, but how does an efficient decoder, which we can extend to a fault-tolerant regime, perform? And here is where the symmetries come in. So I would like to briefly talk about the symmetries in the XZZX surface code. And imagine one stabilizer here. And what I'm going to do now is multiply by a diagonal of these XZZX stabilizers. And the end result here is a double diagonal of Z operators. We call this a symmetry with respect to the error model where only Z errors are being applied, because any error from that model trivially commutes with this symmetry. The conservation associated with that symmetry is an even number of defects along that symmetry. What that means is that when we're performing minimum weight perfect matching, we really only need to look at these 1D diagonals. So if you unwrap these 1D diagonals and lay them out on a line like this, it's very obvious that you're decoding multiple copies of the repetition code, which is a classical code with a threshold of 50%. And therefore, in the regime where bias is infinity and only Z errors are occurring, the threshold of the XZZX surface code is indeed 50%. In practice, for finite bias, where X errors and Y errors are now occurring with some small rate, but are still occurring, the symmetry along the Z diagonals is now violated. And what we do in this case is we favor matching along the Z symmetry diagonals and penalize matching along the opposite diagonals, where the favoring and penalization there depends on the rate at which X and Z errors are occurring, and that itself depends on the bias of the noise. So here you can see the thresholds for, so these are code capacity thresholds where measurement errors are assumed to be non-existent. And I'm plotting the bias of the noise on the x-axis. So a bias of 100 is approximately the point where Z errors are occurring 100 times more often than X or Y errors. And I'm plotting the threshold on the y-axis. You can see that even with a practical minimum weight perfect matching decoder, we're able to trace the hashing bound for high biases. And again, I'm comparing it against the tailored CSS surface code, which previously held the records for the highest thresholds for bias noise. We can readily extend a minimum weight perfect matching decoder to the fault tolerant regime, where we now assume the stabilizer readouts to be faulty, failing with some probability Q. What we do to the code here is we measure the syndromes multiple times and stack them up in a 3D volume to form what we call a 3D syndrome volume. And then match along space-like direction, but also along time-like direction to take into account the fact that we now also have measurement errors. And here are the thresholds in the fault-tolerant regime. Again, you can see that the XZZX surface code threshold exceeds the previous tailored CSS surface code thresholds and are actually very high, so above 5% for biases more than around 10. What I'm also plotting here is the extrapolation of the standard decoder, which doesn't really take into account the correlation between X and Y errors, and simply performs minimum weight perfect matching in that way, in the standard normal CSS surface code. Having said that, thresholds are good, they're important, but we also would like to achieve a target logical failure rate with as few physical qubits as possible. What that means is that below threshold, we want to be falling down very quickly in terms of logical failure rate with the addition of as few physical qubits as we can. Now, for the standard surface code, we can write the logical failure rate scaling in this way, where a little piece of probability on any one qubit. Omega here is the weight of an error operator. So here will be 3. So it's a number of qubits where an operator non-trivially acts on. And the n fail omega here is an entropy term counting the total configurations with the same weight omega, which would lead to failure. At very low p, physical error rate, the term that dominates this sum is the weight d on 2 errors. So for a size 6 surface code, this would be weight 3 errors, like the ones I'm showing here. The reason why this would be this syndrome can lead to an error is because we can either match inside the lattice or we can match around the lattice, and they're both equally probable, and the minimum weight perfect matching decoder will not be able to tell which is the preferred correction. Now, Ignoring the entropy terms here, to leading order, the logical failure rate of the standard surface code dictates as p to the power of d on 2, where d is the distance of the code. I'm going to show now that we can increase this logical failure rate scaling with the XZZX surface code. First, in the regime where only Z errors are occurring, if we slightly tweak the code to make it an L by L plus 1 code, the only logical operator in this code under this noise model is one where every single qubit has a Z operator acting on it. And the weight of this logical is no longer of order D, but is now of order N, where N is approximately D squared, is a number of physical qubits that we have in the code. And therefore, the logical failure rate scales with what we call a quadratic boost, because it no longer scales as p to the power of d on 2, it's now p to the power approximately d squared on 2. Now, this is only in the case where we have infinite Z bias. When we introduce smaller rate of X and Y bias, there are also X and Y errors. There are also other logical operators which are no longer of order N. However, we still detect this quadratic scaling or traces of this quadratic scaling at finite bias for very high biases and p-values very close to threshold. So that's what I'm showing here. I'm plotting code distance against logical failure rate. And I'm plotting here against a quadratic ansatz and against a linear ansatz in the dotted line. And we show more explicitly in the paper, where you can see the equations, that the fit to the quadratic ansatz is in better agreement with the data compared to the linear ansatz. Now, when we go to lower P and more moderate biases, we're back to the case of the standard surface code, where a weight D on 2 error will lead to failure. So does that mean that we cannot gain an improvement in scaling in this regime? No, we can still gain a slight improvement based on the bias of the noise, because even though we have a D on 2 weight error leading to failure, this D on 2 weight error can be decomposed into D on 4 high rate Z errors and D on 4 low rate X errors. The high rate errors make the logical failure rate scale as p to the power of D on 4, but the lower rate errors, because they're suppressed by the bias of the noise, they introduce this factor 1 over eta, 1 over the bias, which is a factor of improvement in the logical failure rate scaling compared to the standard surface code. Now, we formed this ansatz and then we wanted to test it numerically. So it turns out that collecting Monte Carlo simulations at very, very low P is actually quite hard. But there is a very cool method due to Bravi and Vargo, which goes as follows. So we want to collect the logical failure rate scaling at very low P. And we suppose that we know the logical failure at some moderate P. And then what we write is a telescoping product here with these ratios where everything cancels and you get back the thing that you're trying to find. The cool thing about this method is that we calculate these ratios and not this p-value directly. Now, to calculate these ratios, it turns out that we can write them in this complicated form, the expectation value of some operator here and here. And we don't need to know the details of this too much. It's all in Bravi and Vargo's paper. But if we plot this numerator, I'm plotting it in blue here, and plot this denominator here as a function of the constant C, where we estimate this expectation value using samples of a Metropolis Hastings algorithm, then the crossing point between this top and the bottom, so when the top equals the bottom, the C value there, well, you can see that if the top equals the bottom, then this cancels and the ratio equals to that C value right there. So we calculate all those ratios in that way. And from that, we're able to calculate the logical failure rate at very low P. And here you can see the agreement between our ansatz, the solid lines, and the data points that we collected using that algorithm. Where these plots are really the same, but I'm plotting it at logical failure rate against physical error rate, and here I'm plotting it against code distance. Okay, so we gain an improvement in sub-threshold error scaling. Now, finally, I would like to briefly make a quick comment on fault-tolerant quantum error correction. And so I'd like to say that in the paper, in the final section, we demonstrate that we can, in practice, maintain the bias in the noise when we do fault-tolerant initialization and also code deformations. Now, maintaining the bias is really all we need to show, because all of these deformation techniques used to implement logic gates, which work for the standard surface code, also work with the XZZX surface code because they are locally equivalent. Finally, these are some new exciting results regarding quantum error correction with the XZZX surface code and the Kerr-cut qubits that I talked about before. These are circuit noise simulations, and here is a threshold for the XZZX surface code under the circuit noise simulations with these Kerr-cut qubits, and you can see that with a bias preserving C0 gate, that threshold is around 2.1%, whereas for the normal CSN surface code, that threshold is around 1.1%. So even when doing gates, we're able to preserve this advantage, this boost by the bias of the XZZX surface code. Now, to summarize, I would like to say that the XZZX surface code demonstrates high fault-tolerant thresholds against bias noise with an efficient minimum weight perfect matching decoder. It has code capacity thresholds which match and appear to exceed in some regimes, even with an efficient decoder, the hashing bound. It also has improved error scaling below threshold. Some drawbacks of surface codes in general is that they have poor rate. In fact, they have vanishing rate because they can only encode a constant amount of logical information regardless of the number of physical qubits that they use. And so what that means in practice is that we're going to need a lot of physical qubits to implement error correction with the surface code. And also, in a lot of these simulations, we're assuming that we have the bias in the noise accurately characterized, and then biasing our decoding procedure to that characterized bias. But what if the noise wasn't accurately characterized? How would the XZZX surface code perform there? That is an interesting question that for future work. With that, I would like to conclude by thanking everyone for listening and thanking my awesome supervisors again. Thank you.